Yeah, we can hear you. We can just about see you.
And you can see
Okay,
the
put it
slides.
in. We can see the slides, put it into presentation mode, and there you go. All right,
Brilliant.
without further ado, I'll introduce William. He's graduated with a BSc and an M research in geology from the University of Portsmouth in 2017. And his master's thesis was focused on granite-related tungsten tin ore deposits in southwest England. Since then, he has been undertaking a PhD on the magmatic nickel copper PGE sulfide occurrences in northern Quebec, and he's going to talk to us today about the Merensky Reef. So, William, take it away.
Okay, thanks for that. So, hello everybody. Greetings from Cardiff in the UK. I hope that everyone has been keeping safe during this pandemic. It's nice to get back to a little bit of normality today. So I'm going to be sharing some quite beautiful micro-XRF and SEM element maps of the Merensky Reef from the Western Bushveld complex. This is something myself, Wolf, and colleagues at SIRA have been working on for a few months now, perhaps even more for the partners of that. So since I have a nice amount of time, my talk's going to take the format of sharing some of these images, highlighting some of what we believe are the key observations in these images, and then talking a little bit about what some of these features may mean for the formation of the Merensky Reef in the final slide. So as a brief rationale to the project, so we've produced high-resolution micro-XRF and SEM element maps of the Merensky Reef at 4 localities in the Western Bushveld complex. So these 4 localities include the Rustenberg, Impala, Cree, and Northern mines. I'd obviously love to share as many images as possible, but in the interest of time, I'll be describing 1 specimen from Rustenberg and 2 from Northern. And then, as I said earlier, we'll summarize the observations in the final slide. So here we're looking at the specimen from Rustenberg. It's approximately 26 centimeters from the base to the top. And what we're seeing here is both sides of this specimen. So we're going to show micro-XRF maps from both sides so you can see the textures the reef is exhibiting on the centimeter scale. So this particular specimen samples the footwall norite, the footwall anorthosite, the lower chromatite, central pyroxenite, upper chromatite, and the hanging wall pyroxenite. What you might see there is that we see this thickening of the lower chromatite up to this sort of pothole-like structure exhibited by the central pyroxenite, which penetrates downward into the footwall. So here we're looking at micro-XRF element map. So all the images I'm going to show today are going to be orientated with the base to the left of your screen and the top to the right, and I'll be describing them from the base to the top. So just to summarize, the dark blue represents plagioclase, the light blue represents clinopyroxene, the dark green represents orthopyroxene, the green sulfide, and the orange chromatite. So in the footwall, the first things we see is these sort of highways of sulfide, if you can see my mouse. So these highways of sulfide that percolate from the lower chromatite through the footwall anorthosite, and they sort of drape or form a layer over the top of the footwall norite here. Here we're looking at sort of this pothole-like structure where we see a concentration of sulfide together with clinopyroxene in the base of this pothole-like structure. I should note that clinopyroxene generally penetrates for around 1 centimeter into the footwall norite, and it always seems to occur with sulfide throughout. So where sulfide occurs, we always see clinopyroxene together with it. And in a moment, I'll zoom in on some of these areas so we can see them in greater detail. So don't strain your eyes too much trying to pluck out the finer detail. We also see this really knife-sharp contact between the lower chromatite and the footwall anorthosite, and we'll zoom in shortly into this in a minute. And the upper contact shows these sort of centimeter scale undulations, which appear to be defined by individual orthopyroxene crystals. So for example, where found by plagioclase, we see this more diffuse margin of chromatite here, finer, more blocky chromatite. And we also see these fan splay almost textures of chromatite as well, almost in line with the peaks of these chromatites here. The pegmatoid is predominantly orthopyroxene with intercumulus plagioclase, but we also see 2 very large clinopyroxene oikocrysts in this particular map. The pegmatoid also has it has the highest proportion of sulfide in all the reef lithotypes we're seeing here, and it also has the coarsest grain sulfide. I should also note that there is actually there's no chromatite mapped in the footwall at all. So in the footwall norite or footwall northsite, we see virtually no chromatite. And again, mostly finely disseminated blocky grains within the pyroxenite, bar some exceptions here with the sulfide and client pyroxene. So the upper chromatite is much more irregular than the lower chromatite. We actually see these very diffuse lower boundaries where it is bound by intercumulus plagioclase, whereas where it's bound by pyroxene, be it ortho or clinopyroxene, we see these much sharper, more compact chromatite seams as well. In the hanging wall pyroxenite, there is sparsely disseminated sulfide throughout, but it is mostly concentrated in the lower quarter of this unit, always together with clinopyroxene, and these sort of lighter green domains of orthopyroxene as well. And that'll be accentuated in the next image. So again, don't strain too much to see this, but always occurring with clinopyroxene together in the units and throughout the reef stratigraphy, actually. So flipping over the specimen, I apologize if there's slight changes in color there, it's just to accentuate different features. So we see similarities and differences. So firstly, we see these sort of sulfide highways penetrating downward through the lower northsite and draping over the footwall norite. We see this knife-sharp contact between the anorthosite and the lower chromatite, with essentially one chromatite grain separating the pyroxenite from the footwall anorthosite at the base of this pothole-like structure. We see the pyroxenite in this case, or that the central pyroxenite is much more regular than the other side, sorry. There's absolutely no clinopyroxene orthocrysts in this particular side. And instead of two continuous chromatite layers, instead we're actually seeing one thickened chromatite layer. And then we see these sort of almost tree-like structures here of chromatite, which defines the upper margin of the chromatite here. And we also see that same undulation here as well, sometimes seeing here defined by those individual orthopyroxene grains. And again, we'll zoom in further to this and inspect these in greater detail. In the hanging wall pyroxenite, again, we see that relationship, that spatial relationship between clinopyroxene, sulfide, and that lighter green orthopyroxene. And we have these darker domains. So hopefully when normality resumes, we can carry out some EPMA or SEM work to look at any compositional changes to see if this is either an artifact of mapping or these are true compositional changes. So I won't speculate too much about what this may mean at this present time. Okay, so actually what I'll do is I'll actually flip between the two faces so you can sort of compare for yourselves and see some of these features if it doesn't make anyone too dizzy. So. Almost the stems of these chromatite trees almost align with the peaks of these undulations in the lower chromatites. So I'll bring attention to sort of these. And anyway, so zooming into the footwall norite here at the base of this pothole-like structure. So again, this white arrow is way up, and that's going to be a continuous feature throughout these enhanced images. So orientate yourselves now. So the orthopyroxene at the base here, we show these sort of sub-rounded shapes with very little intercumulus rims surrounding them. As we go upward and approach the footwall anorthosite, these intercumulus rims become bigger. And at the base of this pothole-like structure, the orthopyroxene grains are entirely these intercumulus structures as well. In this trough-like structure, we see sulfide sort of concentrating towards the base, again, together with this brighter blue clinopyroxene here as well. Whereas elsewhere in the norite, footwall norite, we see there's actually very little clinopyroxene and very little sulfide elsewhere. So panning upward towards the contact between the lower chromatite and the footwall anorthosite, we see these sort of sulfide highways again traversing through the footwall anorthosite. We see this intercumulus clinopyroxene penetrating approximately 1 centimeter downward into the footwall anorthosite. And what's quite beautiful in this image is the textures exhibited by the chromatite. So usually at the base of the lower chromatite, where it is hosted in plagioclase, we see these vermiform or dendritic chromatite crystals that have been described by a few authors in recent years. We see these mostly concentrated at the base, but they do occur further up in almost patches as well. Again, as you can see, there's no chromatite in the footwall as well. If you see, there's no orange specks anywhere below. This contact is knife sharp at the grain scale. Whereas hosted in clinopyroxene, so here I'm outlining a clinopyroxene grain here. The chromatite hosted within this is much more rounded, it displays much more annealed structures as well. And we'll pan up and look at the chromatite at the top of this margin in a minute. And I see there's actually some orthoperoxene as well together in this with sulfide as well. So here, for example. Okay, so panning up, here is one of those chromatite tree structures. I'm highlighting with the mouse here, and these are some of these undulations we see in one of the maps. So generally, the chromatite hosted in this plagioclase is more blocky, it's not finer grained, where it's hosted in orthoperoxene, for example, except for the interior margins of these undulations here, which is much more rounded and blocky chromatite crystals. See, sulfide is distributed pretty much throughout. So we see intercumulus sulfide in the upper chromatite here, downward into these undulations of the lower chromatite. So just that image so good. Okay. So in addition to the element maps, the XRF maps, we ran a traverse through the footwall. It's hypothesized that the anorthosite is potentially a rest site of melting. If this were the case, one may expect to see calcium enrichment as we approach the reef. And from this particular traverse, we see no calcium enrichment. So it may not be a rest site as some models suspect. Okay, so moving on, we're looking at now the same specimen, but rather than the silicates, we're looking at now the distribution of base metal sulfides, again from the base to the top, from left to the right. In this image, the light blue is pyrrhotite, the pink is pentlandite, and the green is chalcopyrite. The dark blue represents orthoperoxene, and less so clinopyroxene and chromatite. What this image highlights really nicely is the distribution of sulfide, particularly in this footwall here. So we see that sulfide penetrates a few centimeters downward into the footwall northside and then drapes over the footwall norite here, and again accumulates in those troughs, and this highlights this really nicely. We see that sulfide is finely distributed throughout the lower chromatite, mostly concentrated actually on the upper margin of that lower chromatite as well. We see that sulfide is most voluminous and coarse-grained in the central pyroxenite, and again finely distributed throughout the upper chromatite, and then concentrated amongst clinopyroxene at the base of the hanging wall pyroxenite. But we do see that these are finely disseminated throughout the remainder, but much more concentrated towards the base. So draw your attention to this. What we're looking at there is the modal abundance of pyrrhotite, pentlandite, and chalcopyrite in both sides of this particular specimen through the stratigraphy. So the anorthosite, the chromite pyroxenite, and the hanging wall pyroxenite. What we can see actually is that the modes of sulfide phases actually changes very little between reef stratigraphy and in fact through both faces as well. If we're looking at the base here, so here's the lower chromatite, the footwall anorthosite, and the footwall norite. We see there's one of these sulfide highways sort of penetrating downward through the footwall anorthosite toward the footwall norite. And actually the distribution of sulfide phases in this particular instance is very similar to what we see in the chromatite, exhibited by this diagram I'm sharing here. In the upper map, so we see one of these chromatite trees again. We see these finely distributed sulfides throughout the chromatite, and then we see a much coarser grained distribution of sulfides in the base of the hanging wall, in the hanging wall pyroxenite as well. So zoom into these and get a finer look at the sulfides as well. So here what we're seeing is this pink pentlandite essentially lines the silicate phases and separates it from the pyrrhotite core. We see that chalcopyrite generally occurs in sort of intercumulus in pockets adjacent to pentlandite and pyrrhotite pockets. Okay. So the final map of this particular specimen, so now we're looking at, again, so pink pentlandite and light blue pyrrhotite, but these red rings represent platinum PGM. So these are all platinum PGM distributed throughout the reef, and we can see at first glance that they're continuously associated with base metal sulfide spatially. There's very few in the upper hanging wall pyroxenite, but they are generally distributed throughout all the reef units here as well. The majority of detected PGM actually occurred in 2 grains, so that's highlighted in this image here. So these 2 grains, which occur in the exterior margin of base metal sulfides. So all of these platinum PGM occur either at the margin of sulfides or just outside the exterior margin of base metal sulfides. So this map here shows the chromatite and going through one of these sulfide highways into the footwall and orthosite. You see that most of these PGM occur just on the exterior margin of sulfides rather than inclusions or else. And we see it finely distributed in the silicates alone as well. Okay, so moving on from the Rustenberg specimen, we're now looking at a micro XRF map of a northern specimen. So this is from the MP2 reef of northern. The stratigraphy is markedly different from what we were just observing at Rustenberg. So the footwall here is an olivine norite. So just to reorientate with the colors, so this lighter green here is olivine, the darker green is orthopyroxene, orange again is chromatite, blue again plagioclase, and some lighter blue in there is cladopyroxene as well. So I'll describe them both together with the sulfide map as well. So so these lighter green olivine, they appear to form some sort of subtle layering, and they have rims of orthopyroxene as well. And we'll zoom in and look at the nature of those rims in a moment. We see chromatite actually in the footwall, albeit very few grains, but quite large grains and sort of distributed throughout the plagioclase rich portion of the footwall. We see that sulfides generally finely disseminated throughout the plagioclase rich portion of the footwall, and sometimes occurring on the margins of olivine grains as well. And again, we'll zoom in and see that feature in greater detail. And again here, so now we're seeing the distribution of sulfides throughout the footwall as well. And there's some similarity to the distribution phases we observed at Rustenberg. So the upper unit is this sort of silicate-bearing chromatite or chromatite-bearing pyroxenite, however you want to name such a unit. But we see these 2 chromatite pods here. We see these olivine crystals remaining here, but we also have an increase in orthopyroxene rims where adjacent to chromatite and sulfide. So we'll zoom into that shortly. Chromatite is finely disseminated pretty much throughout the intercumulus plagioclase, together with sulfide. It seems to have some sort of spatial relationship in this particular instance. And we have this upper chromatite pod within a basically entirely intercumulus plagioclase as well. And then we'll zoom into the distribution of sulfides in a moment. So zooming into the footwall again, the white arrow indicates way up. So what we can see first is these olivine oikocrysts as well, and we see these rims of orthopyroxene. What's interesting about the rims here is that they continuously occur on the upper margins of the olivine grains. It's not a universal feature. There are some that are exceptions to this, but generally the orthopyroxene rims are most abundant and thickest on the upper margin of these olivine grains as well, here, as I'm circling now. See that sulfide again is finely disseminated throughout the plagioclase rich portion, and it always seems to occur within the orthopyroxene rims and never really as inclusions within the olivine. So we see it with the orthopyroxene rims, as I'm circling now as well. So now we're still looking at the footwall now. The blue is those olivine orthopyroxene crystals there, and the red now represents flogger pipe. So you see there's actually quite a large portion of very fine-grained flogger pipe. It appears to be oriented. So throughout this particular map here, it seems to be oriented from the top left to the bottom right of your screens there throughout. And it seems to, albeit concentrated in the plagioclase, it does seem to occur on the margins of olivine as well, together with those orthopyroxene rims as well. Okay, so panning up the sample slowly, now we're looking at the base of that lower chromatite pod earlier. So we see that chromatite is sort of disseminated throughout the intercumulus plagioclase, but we do see very small rounded inclusions of chromatite within these olivine crystals as well. We see that where chromatite sort of circles these olivine crystals here, we have a much thicker rim of orthopyroxene and a more resorbed olivine core. And we also see the same sort of relationship between sulfide and orthopyroxene here, for example. So we see sulfide in contact with orthopyroxene here, and again here, here, and also down here as well. So now looking at the distribution of base metal sulfides in that same chromatite pod. we see that sulfide is pretty much the primary intercumulus phase of this particular chromatite pod as well. And we have a fairly even distribution of pyrrhotite, pentlandite, and chalcopyrite within this particular specimen as well. We actually see sulfide occurring within the sub-rounded inclusions in chromatite, as well as forming the outside of the chromatite crystals as well. We generally see a large portion of pentlandite as well, just outside of this chromatite pod here as well. Okay, so now we're looking at an SEM element map of a footwall norite from Northern. This is a different sample, but essentially the same unit. So again, we see these olivine crystals with these orthoperoxine rims. The blacked out phase in this particular sample is plagioclase. Red is pyrrhotite and green is pentlandite. So again, we see these olivine orthoperoxine rims. No particular orientation of the rims in this sample, but it is only a thin section, and perhaps a larger scale would be needed. But we see again a fairly even distribution of pyrrhotite and pentlandite throughout the plagioclase rich portion of the sample. And again, we see it concentrated within those orthoperoxine rims of those intergrowths there, as we're seeing here, for example. You may see in this particular map as well is these purple phases, which represents phlogopite. So again, phlogopite shows a similar distribution to the sulfide in that it is concentrated in the plagioclase rich portion, as well as in the orthoperoxine rims surrounding the olivines, as we're seeing sort of here with orthoperoxine, and again here, here, and here as well, and a few places throughout. So this red box, these images to the right of this red inset here. So looking at the plagioclase of this particular sample, we see a sort of a faint layering here, and we actually see subtle reverse oscillatory zoning in the plagioclase. So hopefully some SEM or EPMA work will be able to quantify the compositions of these plagioclase and quantify the zoning in this plagioclase. What it seems to be is that we have these sort of quite thin calcium rich cores and more calcium deficient interiors as well. From that same map, we're also looking at purple phlogopite and yellow sulfide now. We see that phlogopite again shares the same orientation around this crystal, and again throughout this particular sample as well, somewhat perpendicular to the plagioclase layering exhibitors here. And again, that's concentrated on the outer margin of those olivine orthoperoxine crystals there within the orthoperoxine component of that. Sulfide in yellow in this map shows the same distribution of phlogopite, often in contact with it actually, and this distributed around that, again, that orthoperoxine rim as well. So this small yellow inset here is what we're going to be looking at in the next slide, which is our final map, and it's what we believe is a melt inclusion. So zooming into an SEM element map of this feature. So melt inclusions have been described by a few authors in the Merensky Reef. And they always seem to be included in olivine orthoperoxine crystals. So what we're looking at here is albites, phlogopites, zircon, and chlorapatite with approximately 4 to 4.5, I think, weight percent chlorine. I have to check the notes. But essentially chlorapatite, and these light blue crystals here are zircon as well. And then this orange here represents sort of finely disseminated sulfide in this particular melt inclusion as well. And we've noted a few of these features at Northern, as well as Rustenberg. We've seen a few of these features always within olivine orthoperoxine grains as well. Great. Okay, so I appreciate I've described a lot of the aspects of the maps there. So bringing some of those key observations together, hope I haven't biased anyone with ideas through that. But so firstly is those chromatite textures. So we see those vermiform or dendritic chromatites at the base of the lower chromatite. We see more annealed or blocky chromatite crystals in the upper margin, generally when hosted in orthoperoxine. We believe these textures are indicative of supercooling textures at the base, as well as in situ growth where chromatite is annealed. We see that thickening of chromatite against sort of the lee side of those pothole-like structures as well, which is perhaps indicative of granular flow or some sort of hydrodynamic process. We see those undulations, those centimeter scale undulations, and those sort of tree-like structures of chromatite in that Rustenberg specimen, which perhaps looks like maybe splitting of a chromatite, perhaps. Something perhaps to investigate in the future. In the footwall of Northern, we saw those olivine oikocrysts that have those upper rim of orthoperoxine, which to our mind is indicative of reaction of silicate-rich melt during downward reactive porous flow. where the percolating melt interacts with preferably with the upper margins of those olivinoid crusts. We saw no change in calcium as we approached the reef. However, we did see some faint reverse oscillatory zoning, which we suspect to be reverse oscillatory zoning. So perhaps this is less consistent with melting and the anorthosite being a restite, but perhaps more in keeping with sort of leaching of alkalis, which Wolf described earlier as well. We see those highways of sulfide that traverse from the lower chromatite downward through the footwall anorthosite, and then they're draped almost over the footwall norite. So we believe this is consistent with sulfide percolating through the site, but that the norite must have been solidified at time of percolation as well, because that's why we see it draped across the top. We've seen a good amount of flogger in the footwall and other reef units as well during our mapping investigations. We've seen hydrous melt inclusions in the pyroxenite, hanging pyroxenite, and the footwall. I've shown one from the footwall today, but we've seen these in a few localities as well, which appears to be indicative of the presence of a volatile rich melt during crystallization. But currently no sort of constraint on the influence this volatile phase may have on the distribution of sulfides as of yet. So we see platinum PGM essentially throughout, spatially associated with sulfide at the margin or just outside the exterior margin of base metal sulfides. Perhaps this is, reflects either resorption of sulfides, which is why we see them just outside of the base metal sulfides, or mobilization of a PGE-rich melt. We don't necessarily see any replacement textures of sulfide in oxides or amphiboles or anything like this. So perhaps the latter is more in keeping with our observations. But it is worth noting that we haven't yet seen any amphibole, perhaps fine-grained or more detailed SEM maps of sections rather than slabs. We may be able to identify more amphibole. We haven't seen any sort of migration pathways or anything for fluids or anything like this. So hopefully further investigation will reveal a little bit more insight into the role of fluids, perhaps. So with that, feel free to take my email and contact me or whatever, but thank you for listening. Stay tuned for forthcoming research as well. I look forward to your questions or discussion. So thank you.
Thank you very much, William. That was a very well illustrated mineralogical talk. I'll open the floor to a couple of questions. Gordon, you've got a question. You've got your hand up.
First of all, I concur. Very good talk. So a couple of quick points. First of all, you made a comment near the beginning that the top contact appeared less well developed or planar compared with the lower contact. It changes depending on what facies of reef you're in. And for example, over the 30-kilometer strike length of Rustenberg platinum mines, we defined close to 8 different facies of reef type. Some with very well developed and absolutely planar top contacts. Others very disrupted top contacts and planar bottom contacts. So it really depends on what facies of reef you're in as to whether the top or bottom contact is more planar than the other. I don't think that it's a critical feature, but it certainly helps to define. And we were able to map out and define resource characteristics for different facies of reef at different mines. The same is true of Amandelbult and Union Section, and indeed Attock. The dribbling of the sulfides down into the footwall is an interesting concept, and there was a couple of internal papers written. I know Ray Brown did a bit of work on it, on the Attock area, where up to 14 meters below the Merensky Reef, sulfide would dribble down into the footwall and would accumulate in patches, forming, as you indicated, what appear to be little mini pothole-like features. But how this dribbling occurs, that remains to be explained, and I hope you'll get to some of that. But I think that you're doing great work in this.